So good evening friends. Once again we have just complete the concept of remaining stress strain diagram. So in the previous lecture that we have seen about the stress strain diagram for ductile material and the brittle material. So here what is the stress strain curve? That further portion we will just take the overview of that stress strain curve, and then we will just go with the various types of the stress strain curve. So basically the stress strain curve are having or classified into the two parts, that is the engineering stress strain curve and true stress strain curve. And there are the various types of the stress strain curves are there. So basically on the classification there are the generally two terms are there for the stress strain curve. One is the engineering stress strain curve and second one is the true stress strain curve, and there are the various types of the stress strain curves are there. So that part we will cover in this particular content. So this particular diagram that we have seen in the last lecture, once again we will take the overview of that. So a stress strain curve for a material gives the relationship between stress and strain. It is obtained by gradually applying the load to the test coupon and measuring the deformation from which the stress and strain can be determined. These curves reveals many of the properties of the material such as the Young's modulus, the yield strain and the ultimate tensile strain. So these things we have seen in the last lecture, how we can be able to calculate the Young's modulus, what is the yield strain and what is the ultimate tensile strain. So this is the just overview of that particular stress strain curve and how basically the stress strain curve has been formed when we are applying the load. This is the realistic what we can say, that animation when we are applying the load, how basically the deformation will be occurred. So this is the particular component and how it has been elongated and how it has been gets failed. So this is the stress strain curve. This is just an animation purpose. Once again we will just go with that particular thing. This is the component. When we are just pulling it, one end it is fixed, so equal and opposite force has been developed over here and that elongation has been started. So this will be the yield point where the plastic deformation phase has been started, and then finally it has been reached to the ultimate tensile strength and then the breaking is occurred. So now the concept with this particular lecture, that is the engineering stress strain curve. So basically what is the engineering stress strain curve that we will see? Suppose consider a bar of original cross sectional area A0 being subjected to equal and opposite force F pulling at the end so that the bar is under tension. So suppose whatever the original cross section area, if it is A0 and which is being subjected to equal and opposite force F pulling at the end, so the bar is under the tension. The material is experiencing a stress defined to the ratio of the force to the cross sectional area of the bar as well as an axial elongation. So here the stress is calculated likewise. The F is the applied force, sigma is nothing but the stress, and A0 is the original area. This will be the sigma, that epsilon term, which is indicating the strain. So strain is nothing but the change in area minus original area divided by the original area. So this is engineering stress strain curve. Now we will just go with the concept. This 0 denotes the original dimensions. Here whatever the L0 A0, that will be indicates the original dimensions of the sample. Now basically the stress is calculated in terms of newtons per square meter, and strain which is not having the quantity, so it is the unitless, that's why it is a denoted by 1. So stress strain curve for these materials is plotted by elongating the sample and recording the stress variation with strain until the sample fractures. So in the previous diagram here we have seen how this stress strain diagram has been plotted, which is nothing but the stress strain curve for any material is plotted by elongating the sample. Here that sample has been gets elongated and the stress strain curve diagram has been plotted. So what is the meaning of engineering stress strain curve and the true stress strain curve? Here it has been indicated. So for engineering purpose, we often assume the cross-sectional area of the material does not change during the whole deformation process. So basically when we are going with the concept of engineering stress strain curve, the material, whatever the area of that particular material, it will not be changed by whole deformation process. So the original area, it has been considered as it is just constant, it will not be changed. But basically this is not true in the practical case, because the actual area will be decreased while deforming due to the elastic and plastic deformation. So when the neck formation process has been started, whatever may be the area will be there, so that area is decreased. So the curve based on the original cross sectional area and the gauge length is called as an engineering stress strain curve, while the curve based on the instantaneous cross sectional area and length, it is called as a true stress strain curve. So this is the basic difference between the engineering stress strain curve and the true stress strain curve. So in engineering stress strain curve, has been plotted by considering the original cross sectional area and the original gauge length, and true stress strain curve, it has been plotted by considering the changes or whatever the area has been decreased, so that changes has been considered. So the instantaneous cross sectional area at the time of fracture and length, it has been considered. So the true stress strain curve, it has been calculated likewise. So due to the shrinking of the sectional area and ignored the effect of developed elongation to the further elongation, the true stress strain are different from the engineering stress strain. So that's why the true stress strain has been different than the engineering stress strain, because it has been considered the change in a area as well as change in a length. So change in area and change in a length, whatever maybe it has been there. So length has been increased and area has been decreased. So here also length, original length to the original area. So that has been ratioed shown over here. So these are the some formulas. So basically how the stress has been calculated, it has been F upon A for the when we are expressed in the engineering stress strain. So F upon A naught is the whatever the change in area. So that has been written in this different format. So sigma t is nothing but the sigma into bracket 1 plus strain. So basically these are the formulation for the stress strain curves. So here the analysis has been suggested the nature of UTS point, the work strengthening effect is exactly balanced by the shrinking of the cross-sectional area at UTS point. So UTS in the sense ultimate tensile strength point. So after formation of the necking, the sample undergoes the heterogeneous deformation, and heterogeneous in the sense the deformation which will be responsible for the exact fracture. So the equations above are not validate this particular thing, and now it has been expressed in this empirical equation, that is sigma t is equal to F upon A nec, and epsilon t is equal to the A naught upon A nec into logarithmic factor. So this is just general mathematical behavior, how the exactly the phenomena has been occurred. So the metals typically at the room temperature having a ranging from 0.02 to the 0.5, that is behavioral change in the coefficient. So that has been considered in this particular equation because of the temperature effect might be there on the material. So this is the difference between the engineering stress strain curve and the real stress strain curve. So this will be having the different kind of that UTS points for the true stress strain curve and for the engineering stress strain curve. So basically the why the difference will be there, So in case of the tensile test, the true stress is larger than the engineering stress and the true strain is less than the engineering strain. Thus, a point defining a true stress strain curve is a displaced upward and to the left to define the equivalent engineering stress strain curve. So this is the difference has been there in case of true and engineering stress strain curve. So basically the stress strain curves are classified into the four categories, and the first category is the ductile material without yield point, then the ductile material with yield point. So in the last lecture we have seen about the stress strain curve for the ductile material and the brittle material. So in this particular lecture that we will just see the concept or the exact types of the stress strain curve as far as the stress strain curve are considered. So the ductile material without yield point, then second is the ductile material with yield point. So for the sum of the material that yield point has been generated, even it is having the ductility, but for the some ductile material that yield point will not be there. Then the stress strain curve for the brittle material and the polymeric material, it is having the different kind of that stress strain curve. So that portion we will see in this particular slide. So first of all, that is the ductile material without a yield point. So here we can be able to see the stress strain diagram for the ductile material without any yield point. So basically the copper, aluminium, so these are the materials which are having, or we can say that is the ductile material but which is not having any kind of that yield point. So basically after the elastic limit, it is directly reaches to its UTS point, that is the ultimate tensile strength, and then the breaking will be there. So the curve shows the rising stress during the plastic deformation because of the strain hardening, and the curve drops beyond UTS because of the necking. So neck formation will be there. The difference between proof stress and the ultimate tensile stress is more with the highest ductility. If the whatever the ductility, if it is higher, so that will be gives us some sort of the difference between the proof stress and ultimate stress. So basically this is the curve that which we have seen in the previous part, and here we can be able to see this is for the low carbon steel or mild steel, and the basic difference in this previous stress strain curve and this stress strain curve, here we can be able, which is shown in the red color, that yield point. So this will be a upper yield point and this will be a lower yield point. So this will be the stress strain curve which has been the yield points, and basically for the low carbon steel or mild steel, these kind of that stress strain curve that we are getting. So the curve is almost similar to the previous curve except the presence of yield point at the end of elastic deformation region. So here the yield point has been occurred, and it is established that the yield point phenomena is exhibits by interstitial solid solutions alloy having the BCC and FCC crystal structures. So basically it has been exhibit in the solution or alloy which is having either the BCC or FCC crystal structure. So whatever may be the these phenomena are concerned. So in ductile material, these two kind of that stress strain curves we are getting, which is having either the yield point in that particular diagram or which is not having any kind of that yield point. So basically that yield point which just gives a phenomena which has been just whatever the plastic deformation, when after the elastic deformation, when some sort of that changes has been there and the strain, whatever the stress has been suddenly dropped down and the strain hardening has been started, and then again the stress has been increased after some sort of that constant revolution and drastic, this here we can be able to observe a drastic change in a stress as well as strain is there, but for this particular zone almost the stress and strain has been dropped, very the strain hardening has been started over here and stress is almost near about the constant phase. So this is the phase change moment from elastic to the plastic region, and when the low carbon steel or mild steel, these kind of the structures we can be able to observe. Now the next is the stress strain diagram for the brittle material. So the curve which is having the three kind of that curves here we can be able to observe. So the curves for these materials may be 1 out of 3. The curves 1 and 3 are the almost linear up. So 1 and 3 curve, it is very similar to the fracture, which is indicating that the plastic deformation preceding the fracture is negligible. So here there will not be any kind of that plastic deformation is occurred in this particular 1 and 3 curves. So after elastic limit, this curve, whatever the stress, it has been constant, and suddenly before any kind of that major plastic deformation or neck formation, that particular component has been failed or that rupture has been occurred. So due to the difference between the proof stress and UTS is here again the negligible. So the example of brittle material stress strain, that has been the cast iron, brass or concrete. So grey cast iron or white cast iron, any cast iron that has been considered under the brittle material, and the brass as well as the concrete. So these are the materials of the or classified into the brittle material. Then this is the last stress strain curve, or this is the last type, which is for the polymeric material. So polymeric material in the sense any rubber material that is natural or synthesis rubbers. So basically the stress strain curve for these kind of that material, normally it has not been considered, but as far as the engineering is concerned, it is having some sort of that practically those, it is not considered under any kind of that metal, but it is important just to go with that particular concept of polymeric material which is having the stress strain curve. And here in this particular stress strain curve, it shows the rising trend very much similar to the ductile metallic material. So rising trend in the sense here, whatever the rising trend it is there, okay, in the ductile material, similar kind of that rising trend here we can be able to observe initially in the rubber, and again it is having the phenomena, the stress whatever may be the developed, that is because it is not taking a much load, but the elongation is more in case of that rubber material, and that's why the strain factor is it gives a very higher value in this case, and this is due to the crystalline structure and do not due because of the strain hardening. So here that strain hardening will not be there, but the elongation is very higher in case of such kind of that material. So the example of polymeric material is the natural and synthesis rubbers. So these are the four types of the stress strain curves. So I hope you have understood the concept of stress strain curve. What is the engineering stress strain curve, that comparison between or difference between the engineering stress strain curve and true stress strain curve. So basically in the practical case, unless and until if it has not been mentioned about the true stress strain curve, ideally we are just going for the stress strain curve, that is the engineering stress strain curve. So the stress strain curves, what is the why it is required, that we have covered in the last lecture. What is the purpose of the stress strain curve, and all those aspects that we have studied in these two lectures in the stress strain curve. Basically the stress strain curve, it is related to the tensile test. So when we are conducting the tensile test, we have to calculate some sort of that properties of that material or some sort of that straining effect. So those straining effect has been considered by or has been calculated by using the stress strain curve. So these are the basically the four types of the stress strain curve. So when we are in the examination, when the types has been asked, you have to just write all those four types of the stress strain curves. Okay, so I think now it has been very clear about the stress strain curve. Now you can be able to plot the stress strain curves nicely. Again, you can be able to write anything about the stress strain curve. So if any kind of the doubts are there, it is welcome for you people to ask it. Now in the next lecture, we will just go with the compression test. So how that compression test has been carried out. So which kind of that machines has been used in the compression test. So those part we will cover in the next lecture. So thank you very much.